Good afternoon. I'm Jay Scott, editor of High Performing Buildings magazine. Thank you for joining us for today's webinar, part of the HPB Supplier webinar series. The series provides information to HPB readers and others about technology for industry professionals. ASHRAE does not review supplier webinar presentations. Nortec would like to welcome you to this webinar on 7 steps to indoor air hydration for health. Today's presenters are Dr. Stephanie Taylor and Howard McHugh, PE. An honors graduate from Harvard Medical School, Stephanie practiced clinical medicine and pediatric oncology and was involved in academic research for over 20 years. Determined to better understand the interaction between patient outcomes and the hospital-built environment, she obtained her master's degree in architecture. After several years working in a healthcare facility architectural design firm, Stephanie founded Taylor Healthcare Consulting. Now an internationally recognized consultant, she works with architects, engineers, microbiologists, and regulatory committees to design and manage hospitals and other commercial buildings to optimize patient and occupant health. Howard has over 52 years of experience in building systems design, construction, commissioning, operation, and maintenance. Currently president of Building Smart Software, LLC, he has been an industry leader in promoting the practice of commissioning and in developing commissioning standards. Howard is the author of more than 500 articles and monthly columns and one book, Managing People in the HVAC and R industry, as well as a contributing author to 4 books and multiple ASHRAE handbook chapters. In addition, Howard is featured as a guest author, speaker, and subject matter expert on several online webinars, podcasts, and an ongoing blog. And with that, we now turn the presentation over to Stephanie. Thank you.
Well, thank you very much for that introduction, and thank you to ASHRAE and to Nortec for sponsoring this, and thank you to all the invisible audience folks that I can't see. Please write down your questions as we move through this presentation so that at the end we can answer your questions and comments. So now let's get started. This webinar is really bringing together the industries of healthcare, clinical healthcare, and engineering, specifically around 7 steps to indoor air hydration for health. So getting started as I try to move my slide. And could you advance the slide, please? Sorry, guys, my slide's not moving. Oh, the slides are advancing. This is what happens when you bring together 2 industries. Sorry, guys. Okay. You know who we are, so let me just skip that slide. So what we're going to talk about today are basically 3 areas. 1, health trends that we're currently experiencing. Number 2, why we need to hydrate the indoor air. And 3, the current climate around humidity. So starting with the current health trends, I'm sorry, I'm having a... And would you mind advancing to slide 5, please? The current health trends that I'm referring to are alarming. In healthcare, people go into the hospital and ostensibly go into the hospital to get better, but unfortunately, there are far too many patient errors and actually new infections that patients acquire when they become an inpatient. A scary statistic is being hospitalized is actually the third leading cause of death in the United States. So going into the hospital causes more deaths than car accidents and coronary artery disease put together. That's just not the way things should be. As we all know, healthcare costs are way too high. Third, interesting, there's an increase in certain chronic diseases such as autoimmune diseases, birth defects are on the rise, and other inflammatory illnesses like inflammatory bowel disease are rising, and we're not really sure why. And fourthly, a lot of or certain infectious diseases are reemerging, things like measles, very antibiotic-resistant tuberculosis, cholera. You know, these infections are on the rise, and we're not sure exactly why, but we need to ask, are we missing something? So Anne, will you press on to the next slide, please? Another thing we need to take a look at is that we human beings in urban environments are basically indoor creatures. Studies show that between our home life, commuting, and our work time, even if we live in a beautiful state, like I live in Vermont, which is gorgeous, but I still probably spend 90 to 95% of my time indoors. Next slide, please. So the relationship between these emerging diseases and the fact that we're indoors so much of the time really raises the question, is there a link? I think there's a lag time on my slide. Are we on slide 7? So if you listen to some of the experts about the built environment and human health, such as Ken Dickerman, who is the AIA designer for the VA system, he says, we shape our buildings, then they kill us. So that's an alarming statement. And like many alarming statements, if we're going to say it or ask a question, we need to be able to answer it. So let's take a look at what we now know about our indoor environment using some new tools. Next slide, please, Anne. So this animation shows particles and droplets in the air that we clearly can't see with our naked eye. So as I'm sitting here in my office talking into the phone, I'm emitting these tiny droplets that carry all the bacteria and viruses that happen to be in my body. You can also see in this animation that skin flakes are being suspended from this engineer or architect's body. So you can see the illumination of her particles from her skin. As this thing goes along, you'll see her digestive tract is illuminated. So all the microorganisms that are in and on in this animation, her body, but all of our bodies are being emitted into the air, and they are resuspended, they travel around. And how that resuspension and travel occurs depends a lot on how we ventilate our buildings. If I can move this along. So what are those droplets? And what are in them? Well, this is an amazing time to be a designer of the built environment, because every time we get a new tool, we get a vastly different view of our place in the world or the universe. When we discovered the microscope, we learned that these single-cell organisms were involved with disease. When the telescope was discovered, to our great human amazement, we were not the only planet in the galaxy. So now, the tool that I'm referring to is, I say, the genoscope. Really, the tools are metagenomic DNA and RNA analysis tools. Maybe you've heard of PCR or the microbiome of your gut. But we now have the ability to actually look at the DNA and RNA fingerprint of all the organisms, whether it's on our body, in our body, or in the air, or on surfaces. So using these metagenomic techniques, we have a much clearer idea of what biological organisms are floating around us. So with that in mind, what have we learned? Well, one thing we learned in 2003, after we sequenced the entire human genome, we learned that each of us, each human being, is by cell number only about 30% human cell. So that's a startling realization. So of our cells, more of us are bacteria primarily, with a few fungal organisms and a few viruses. But we are more bacteria than we are human. So what does that mean for the built environment? So again, I'm not sure my slide's the same as yours, but so if you think about it, it's not too hard to imagine that as we move around our buildings and our rooms, our offices, our homes, all of those microbes that are coming out of our body and off of our skin are going into the building. And conversely, organisms that are in the building from previous occupants are relating to us. So there's a very active communication between humans and the building. Prior to using these DNA techniques, we were using tissue culture, petri dishes alone to determine which organisms were in the environment. And so while tissue culture is still really valuable to tell us which of the organisms are alive, they only capture about 10% of what's in the environment. So that we now know about the other 90% of organisms that are all around us. So again, what's that have to do with engineering, and what does that have to do with our health? So this slide shows a really fascinating study done by the University of Oregon. And so if you look carefully at the axes of this graph, you'll see on the x-axis down at the bottom, you have phylogenetic diversity. So as we move to the right, all of the diversity of the organisms that we're recovering from a building become more diverse. And now if you look at the x-axis moving upward, the higher you go on the y-axis, the higher you go, the more similarity those organisms have with known pathogens or things that cause disease. So if the audience could actually speak, I would ask you to interpret this graph, but since I have to do all the talking right now, I'll tell you. So the mechanical, or the red dots, are the least diverse and the most pathogenic, or most related to pathogens. And as you move towards more outdoor ventilation in your buildings, you get a more diverse group of organisms, and they're less associated with pathogens. So essentially, you want to be around the blue dots. So let's take this data, and let's think about what is the most important building metric what's the most important performance metric for a building. So currently, when I read about buildings or think about buildings, I think about energy consumption. If it's a hospital, I'll read about their profits. If it's an operating room, and trying to figure out how to manage the air, usually it's focusing around clinician happiness, clinician comfort. But what about another metric? What about human beings in buildings? What if we think about how do we design and manage a building for the human occupants? So we actually did a study with that focus. So we looked at a hospital that was built in 2013. It was brand new when we started the study. It was about a 270-bed hospital, LEED silver, had a green roof, 24 operating rooms with transplant units, state-of-the-art, all single rooms with vestibules. So we went to that hospital, and we identified 10 identical patient rooms with two populations of patients. They were all single rooms with vestibules. And over the course of 13 months, we monitored these following indoor parameters. So we looked at CO2 levels, lighting, temperature. We monitored staff and visitor hand hygiene behavior, room air changes, room traffic in and out with an infrared beam, relative and absolute humidity, outdoor air fractions, and room pressurization. So over 13 months, we had about 8 million data points. So we related those data points to, in keeping with what we've been talking about, we related those data points to patient infections, to new patient infections, known as healthcare-associated infections, or HAIs, used to be called nosocomial infections. So just to sort of re-summarize, we measured all of these parameters in the patient room And then through a statistical analysis, we related them back to patient outcomes, specifically new infections. So just stop for a minute and think to yourselves or write down, what do you think the most important indoor parameters were when it came to patient infections? So which of those things that we monitored do you think was most related to patient healthcare associated infections? So I'll just pause here while you can think about it. Well, what we found was startling to us. It was so startling that we didn't believe it, and we went back and did another analysis. So these are the results. We found that on the x-axis, we moved from the winter, starting in actually January, through the summer and back to the following winter. And on the y-axis, we show the indoor relative humidity. So the blue line shows the average for all 10 patient rooms. And the red columns are the number of healthcare-associated infections in those 10 rooms. So it's not very subtle here. You can see clearly that as the relative humidity in the patient rooms goes from 32 up towards 42%, the number of patient infections goes way down. So you can say, okay, this tells me I should have my surgery in the summertime. I mean, that's probably what I would do, but I would also think about how are we going to manage the indoor environment to decrease these infections. So these results show us that as the relative humidity climbs up towards 40–42%, patient infections go down. And that was statistically significant to less than p less than 0.02. And again, if you have questions about the analysis, please write them down and we can talk about it. Because the data mining isolated this as an independent variable. Okay, so where do we go from here? Why is indoor air relative humidity important for people? And what does it do to the microbes that we saw were floating around the room? Well, one thing we're learning is that indoor air, dry indoor air, is actually terrible for human beings. So as we go through this, just think about your own experience on the airplane or if you're in a dry hotel or office building. So even mild dehydration is harmful for people. And those of us who sit in a room with a relative humidity around 20%, unless we have a continuous IV dripping into our veins, we become clinically dehydrated in about 8 hours. And at this point, 1% dehydration, you're not even thirsty yet, your urine hasn't begun to darken, so you don't even know that you're dehydrated. Actually, most of us probably exist at this state a lot of the time. But with even mild dehydration, there's an impact on your corneas, our skin becomes cracked, wound healing is impaired. The military has shown that actually our brain function is challenged. We're more vulnerable to infections and asthma, and blood clotting is more rapid. So for instance, heart attacks and strokes are worse in mildly dehydrated patients. So just taking a look at the results of some of these studies. This slide, which I'm trying to bring up, this is sort of a graphic display of a study done by the military showing, Anne, are you on slide 23? Great. So this slide depicts a study that shows that even mild dehydration impairs our brain volume, and this has consequences for our cognitive functioning, for our memory, for our hand-eye motor coordination. So on the left, you see, this is the same person, functional MRI. On the left, you see this person after about 20 hours at 30% relative humidity. And you can see the volume of the brain has decreased. The brain is about 85% water. And the circle shows that the neurotransmitter activity is diminished in this drier indoor environment. As compared to the right, where the same guy is at 50% relative humidity, you can see the brain volume is more euthymic, it's healthier, and you can see that the neurotransmitter activity is normal. So that's the brain. What about our skin? So clearly our skin is important. Our skin is important to protect us from the outside environment. It's important for wound healing. Our skin as a barrier helps train our immune system, protects us from infections, and helps preserve our internal water homeostasis. So what happens when we have dry skin? Even dry as in you've been on the airplane for a 4-hour flight. So this slide shows at the top the outside world. So this is an illustration from Nature, from the journal Nature. And when your skin becomes even a little bit cracked, antigens and microbes from the outside world can get through the epidermis and down into the deeper dermal layer. And this begins an inflammatory process. Most of us aren't aware of inflammation, of mild inflammation in our skin. But if anyone has eczema or any other dermatitis, you might experience that those symptoms are better when you're in more hydrated or humid air. So dry air is really hard on our skin. Let's go a little bit deeper into our body. What about our respiratory tract? So all of us have, from about our throats down into our lungs, these little hairs on our respiratory epithelium. These little hairs are constantly waving upward in a thin layer of mucus. And if that thin layer of mucus that lines our respiratory tract becomes more viscous, even by as little as 6%, those little ciliary hairs can't work. They can't, and the reason we have them is to keep particles from settling down deep into our lungs, where if it's bacteria, it could easily cause sepsis or other sorts of lung diseases. So in dry indoor air, that mucus becomes more viscous, it becomes thicker, and bacteria and particles can reach the depths of our lungs much more easily, and that's a bad thing. So that's dry air is really bad for human beings. What about all of those little bacteria and viruses that are floating around? What does dry air do to them? So this is an MIT video, a strobe video of a person coughing, which is kind of gross, but it tells a story. So how do I play this again? Well, anyway, hopefully you remember the video. So what indoor air parameters determine whether or not those infectious particles are going to reach the next person? Well, dry air, pathogens or microbes that cause disease love dry air. They can travel further. Many viruses and some bacteria are actually more infectious when they're airborne, when they're traveling in these little droplets. And thirdly, in dry air, you can have a previously clean surface that will then be recontaminated by organisms settling out of the air. I mean, if you think about it, we live in a three-dimensional world, so things that are on surfaces are going to go up into the air and then resettle. So the more turbulence and the drier the air, the more things are going to be suspended and then resettle and contaminate the surface. So for these reasons, pathogens do very well in dry air. So for example, this slide is showing that as I'm talking, droplets come out of my mouth and everyone's sitting around breathing. Droplets are coming out of you with a diameter of about 100 microns. And then depending on how dry your indoor environment is, those droplets are going to shrink to establish equilibrium with the outdoor environment or the room environment. So if your air is around 20%, those droplets are going to shrink to about 0.5 micron diameter. At that tiny size, they become known as droplet nuclei, and they can remain suspended in your room. They can fly through the HVAC system, and they can reach other people, this study showed 41 hours later. It actually can be a lot longer than that. So these tiny droplets shrink and float around when the air is dry. So if you're in a hospital as a patient and one of your visitors or family members comes in and coughs, if they're sick, those little infectious droplets if the room is dry, they go up into the air, they go through your ventilation system, they're recirculated, and they can recontaminate other surfaces. So dry air increases the likelihood that somebody else is going to become infected. So this kind of is on another scale. This next slide, hopefully you're seeing it. And thank you. So on another scale, this is just a climate study that I wanted to show you. There's an area of Africa known as the meningitis belt. And if you read the literature, these meningitis epidemics occur when there is dry, hot weather that comes into the region. And the journals say that the bacteria spread through the air when the outdoor humidity is low. And once that outdoor humidity exceeds 40%, the epidemic ends. So this is just like one study that shows another relationship between dry air and a bacterial disease. So as you're listening, just think about, okay, the flu season is in the winter. And a lot of us think, well, is that because the air is cold? But we're now beginning to separate temperature and humidity. And we're finding that flu season and viral transmission is also very dependent on dry air. So what should we be doing? Well, actually, and if people in the audience, people are part of ASHRAE, you'll hopefully recognize this Sterling chart. So in 1985, a study was done using 12 clinical papers showing that if you look at the black areas, which are bad symptoms, hopefully you'll be able to read it, but the black sort of V-shaped things show ozone, allergies, respiratory infections, viral and bacterial problems on the left, and the same things plus mites and mold on the right. And what this chart is showing is a sweet spot between 40 and 60% relative humidity, where symptoms from these problems are at an all-time low. So 40 to 60% indoor relative humidity is great for humans, and it inhibits or sort of neutralizes the infectivity of many pathogens. So right now, our indoor environment is not, in most buildings, in the wintertime anyway, is less than 40%. So even if we could aim for 45%, that would be an improvement. But let's see, I'm trying to get slide 34. But the great debate goes on. As a clinician, I say we need indoor air humidification or indoor air hydration between 40 and 60% relative humidity. Most building people say, buildings don't care. The drier, the better, for a number of reasons. So there's sort of this push-pull debate going on. But the studies show if we're thinking about human occupancy and human health, whether it's a patient in a hospital, an office worker, or a student, or all of us in our homes, 40 to 60% indoor relative humidity is optimal. So now I'm going to turn it over to Howie McHugh, so he can tell us how to do this.
Thanks, Steph.
Hey, Howie.
Okay, so as Steph has stated, education is teaching us that indoor air hydration for health is increasing. Occupant health should be the #1 metric for building performance, second to none, meaning not cost per square foot, not BTU per square foot per year. No other metric should be as important as occupant health. Sustaining peak occupant health requires continuous building performance. Building management and building operators must commit to long-term indoor air hydration for health success. Designing and construction is only the tip of the iceberg. Just like the example, and I've used this in the past, of building operating costs over the life cycle, the tip of the iceberg, which is about 15 to 20% of the whole iceberg, is first cost. Everything below the water is operating costs over the life of the building. Indoor air hydration for health is a similar commitment that goes below the waterline of this iceberg analogy. Design, construct, operate, and maintaining the HVAC systems per the O&M manual, maintaining the equipment devices per the O&M manual. These are all critical to continuous and reliable occupant health within a building. Example of operating an HVAC central air system is noted below here, and from an operating point of view, here is what first must happen. If it's an existing building, retro-commissioning the system, units, and components are required. If it's a new building installation, commissioning the system, the units, the components are required. After owner occupancy, continuous commissioning or recommissioning on a scheduled basis will assure peak #1 metric performance pertaining to occupant health. And in this example, I'm using the system and noting humidifier as one of the components, since this discussion is based on indoor air hydration. Without continued commissioning or scheduled recommissioning in place, maintenance is the next, with continued commissioning and scheduled recommissioning in place, maintenance is the next mandate. An example of maintaining an HVAC central system with Supply Air Humidifier, as well as other components, begins as follows. In an existing building or a new building, make sure there's a CMMS system. CMMS is Computerized Maintenance Management Software System. And within it, there should be predictive maintenance work orders of certain components and scheduled maintenance work orders for the unit and all its components. Going back to commissioning of an HVAC central air system, there must be a basis of design document, and that's to begin the whole process way back in the design phase. With that, what follows is the writing of a functional performance test narrative for the HVAC system. And the actual functional performance test on site when the system is been furnished, installed, balanced, and that commissioning test demonstration includes certain components. From a maintenance point of view, a sample predictive maintenance humidifier example would be to, through the building automation system, continually monitor the steam pressure at a humidifier to assure unit performance. If the steam pressure is not at the design, and it's, let's say, half, it affects the capacity of the humidifier. So it's important to be assured that the system is working correctly. Another predictive approach to the continuous monitoring of steam pressure at a humidifier is to assure the unit strainer is not getting clogged. When you're doing predictive maintenance, it's continuously providing feedback. For someone not doing that, and if it's a critical thing such as steam pressure, you wouldn't know that until you went out to maintain the humidifier and clean the strainer. So these are just two potential continuous maintenance data inputs. A sample scheduled maintenance work order will look like this. A CMMS system, equipment database, will include work orders. And using our example of the steam humidifier, the steam humidifier work order would include the following. Safety instructions, such as shut off the steam to the humidifier before maintenance is performed on the unit. If it had an electrical component, you'd do lockout, tagout as well. The work order would also provide special instructions, such as special tools to bring. You don't want the person going all the way out to the other end of the building to service the humidifier and find out they don't have all the right tools. And then tasking is another part of the work order. And it's various tasks that would be performed monthly, quarterly, semi-annually, or annually. And it would include tech time. So that, for example, to go out and do maintenance, one of the things is to wipe down the whole unit. You could budget 5 minutes to clean the humidifier. This budgeting also helps to create what the operating preventive maintenance annual work order or annual work budget will cost. So to summarize it, collectively with owner occupancy, continuous commissioning or scheduled recommissioning is critical to keeping the systems operating as designed and to be assuring that occupant health is being taken care of. Along with proactive maintenance will also contribute to achieving the #1 metric goal, which is occupant health. So the tip of the iceberg, below the waterline, it's up to the building owner and building operator to budget and be proactive in operating the HVAC systems continuously to assure that the building is going to be safe and it'll be good for the occupants in their health. And it'll also help to extend the useful service life of the equipment when you're proactive. So I'll give it back to you, Steph.
Great. Thanks, Howie. It's always nice to have somebody who actually knows how to get these things done. So now we know that indoor air hydration or indoor air humidification is really essential for occupant health. So as we consider that metric along with energy consumption and first costs, maybe many of you are thinking, well, in my experience, the only good humidifier is one that's turned off. Or maybe humidification is the first system to go in the design. I've heard a number of different responses to this. But let's take a look at what really gets people's attention, whether it's the seller or the customer. Rightly or wrongly, it's money. So with that in mind, let's take a look at that hospital where we did the study. And we clearly saw from that study that if you properly humidify the patient room or hydrate the air, it's associated with fewer of these new infections, healthcare-associated infections. So this chart shows the 6 most common nosocomial or HAIs, urinary tract, surgical wound, catheter-related sepsis, ventilator-associated pneumonia, MRSA, and Clostridium difficile. So those are the 6 most common infections. That hospital, we did the study, in 1 year, lost over $15 million in non-reimbursable costs. And so, I mean, $15 million is a lot of money. And that doesn't even begin to account for litigation and other fees that we don't really see reported very transparently. In addition to losing that money, they had 11,000 patient bed days tied up with non-reimbursable patients. So for a hospital, I mean, that's a significant cost. That study was done with, clearly with hospitals. But if you do an ROI of office worker productivity with good indoor air hydration, if you can account for lower absenteeism and greater productivity, again, properly hydrating the air provides a financial benefit as well. So this slide shows a barely legible ROI for a hospital with just 20% decreased infections, 20% fewer healthcare-associated infections. And if you put in a very expensive, I think an overly expensive gas system, accounting for, say, OR downtime and space non-utilization, you still are going to have an ROI of over 500% in the first quarter. So there is a very good argument from a financial perspective of humidifying your building, your hospital. So if the listeners find this concept interesting or something that they want to learn more about or be involved in, and could you put on slide 47, please? Maybe it's already there. We are having our second healthcare symposium in Boston at Harvard Med School this May 9th and 10th of 2018. Last year we had a very successful event. This symposium brings together hospital CEOs and healthcare leaders, clinicians, brings them together with microbiologists, engineers, and architects to begin to talk about managing the indoor space and managing hospitals specifically, with the idea that our most important building metric is patient outcomes, student performance, employee productivity, but overall that the human being is a metric that we need to more fully consider in managing our buildings. So thank you. I'm not sure if the last slide is up, but if it is, this is just Howie and me having fun in our respective states. On slide 48, that's me hydrating the air and Howie's throwing a very large droplet at something or another. So thank you, and I hope this has been helpful, and I hope you have a lot of questions. So now let's turn it over to the question and answer time.
Okay, thank you, Stephanie and Howie. And please submit your questions here. We may not get to read them all, but we will make sure all questions are answered. It may be in a follow-up. But let's just take some of the more common ones here. And so one of the, as I'm reading through here, how does, I guess, Dr. Taylor or Stephanie, how does this relate to time of year that when the flu is prevalent? Do you think low percentage relative humidity allows the flu to spike?
Yeah, so that's a great question. And the flu season clearly is in the winter in cold climates. So you might think, okay, well, maybe that's what's accounting for the higher infections in the winter. So our study did not show a correlation between visitors and patient infections. So people weren't bringing the flu into the patient room. We did not find a correlation between outdoor air fractions and infections. And thirdly, the patients experience mostly bacterial infections rather than viral infections. The flu is a virus. So, I mean, that's a great question, and we now have 3 other studies to more fully answer, whether or not the flu season influence these outcomes, but it looks like from our current study that that was not the deciding factor. But I mean, that's a great question. And if you have any thoughts about it, please email me and we can figure out how to continue to do research on that.
Okay, thank you. And the next question regards, I guess it could be Howie or possibly Stephanie, but how many air changes are typically required to conform to healthcare environment and conditions in the building envelope?
Well,
I don't know.
I'll take a stab at that. So
Yeah.
right now, oh, okay, Howie, you want to do that?
No, I was going to say, yeah, because you've got different thoughts on that versus what the ASHRAE guidelines talk about. So go ahead.
Well, so what I was going to say is, again, not to sound like indoor air relative humidification or proper humidity is the answer to all problems, but we are finding that you can turn down the room air changes by at least 10% and saving energy from decreased HVAC system usage. You can turn down air exchanges by about 10% and still have a room that's just as clean as it was with a higher air change rate, maybe even better. So right now, patient rooms are supposed to be at 6 air changes. ORs are as high as 20. But again, if you properly hydrate your air, you can turn those rates down and still have a very clean environment.
Okay. So I think this one would be Howie. What should be the fresh air percentage? Is that something that's standardized?
Well, again, the ASHRAE guidelines indicate how much outdoor air should be introduced into, say, a patient room versus an operating room. I think recent studies are focusing on how to reduce that outdoor air. I know that, say, in an operating room, it used to be standard that you ran it 24/7 at anywhere from 15 to 25 air changes over the past several years. But someone finally was able to come up with you have an occupied and unoccupied period. So you could reduce it to something like 6 air changes when the space is not being used, as long as you do it and keep the room under positive pressure. So that doesn't give you a real answer at this point, other than the guidelines do indicate what percentages they should be. And to divert away from them, a designer would have to have some good reasons to justify it. And I think with future studies, and even with the studies that Stephanie's been working on, there may come out of this data to reduce that amount of outdoor air.
Okay, thank you. I'm getting a lot of questions now. Won't be able to get to them all, but 1 or 2 more here. So for Stephanie, concerning the correlation of humidity and infections, how can we be sure that it's not due to this temperature?
Well, again, that's a key question. In our statistical analysis, we put all of the variables in, and what the results showed was that relative humidity and not temperature was related to patient outcomes. We have some other studies looking at mortality rates that are related to dry air, not the temperature. So again, that's a question that probably I can more easily answer with some references via email.
Okay.
But the beauty of statistical analysis is you can isolate one variable.
Good. And I guess another question regarding this study as well. Are there any studies looking at relative humidity levels above the 42%?
Yes. There's some really good studies out of Japan that look at 50% relative humidity in patient areas. and relate that to a more diverse microbiome. So yes, there are other studies that look at the whole range between 40 and 60% and show that it's beneficial.
Okay. We have a couple. What about UV lights? How does that play into this?
I mean, so again, I know there are other technologies
yeah.
that are out there for, so the thing about UV lights, they operate somewhat differently in that they ostensibly eradicate all particles or all living particles. We're not sure what the relationship is between, proper humidification and UVC specifically. There's no adverse interaction, but we don't know if, for example, if indoor humidification would actually enhance the biocidal effects of UVC. So I think that the short answer is I'm not really sure.
Okay. And this one for Howie talks about humidifiers and maintaining humidifiers. And is there a concern with Legionella with the use of humidifiers?
Yeah, there's always a concern whenever you have moisture, but that's part of the routine of doing, proactive maintenance. Actually, right at the humidifier itself, there's usually a high limit so that when the humidifier comes on, it just doesn't flood the ductwork and then have a wet surface in there and the air blowing across and taking that downstream. There's, back at where the water is coming in for a steam humidifier, there's got to be maintenance to make sure the quality of water is correct in that. So yeah, it can't be overlooked for sure.
This is Stephanie. I know that, for example, Sloan Kettering is using the new adiabatic system for humidification in their, and Sloan Kettering is an oncology, cancer hospital. So there are some really new safe solutions that include both low energy and hygiene steps.
Okay, thank you for that. And last one, I guess, Howie or Stephanie, are you seeing hospitals make changes based on this data?
I'll let Steph answer.
Hospitals are probably the hardest. It's probably the hardest place for any change to be instigated. We're having better success in assisted living facilities because the regulations are a little bit less stringent. But we're seeing a lot of interest in this and a few early adopters.
Okay, that's it for the questions. If you have further questions, please submit them online. We'll make sure that we get Howie or Stephanie to answer those. And Stephanie, you want to take over from here?
Yeah, well, I just wanted to thank everybody for listening and participating, and I hope that you now at least have some new thoughts about dry air versus properly humidified air. And again, we need all the research and all the data we can get. So as individuals, put a hygrometer in your home and see and measure the humidity, correlate it to how you feel. And then if you decide to humidify, again, collect some data on yourselves, on your family, on your workplace. This is really an exciting new tool that we have to manage buildings for humans. So anyway, I just want to say thank you.